positive direction in a circle, okay? That's our positive direction. Which is kind of interesting rule. And most of you are very familiar with the right-hand rule when you're driving in a screwdriver, right? Righty-tighty, lefty-loosey. If you happen to remember the little thing, if I'm going to do righty-tighty, lefty-loosey. And when I do the right-hand rule, what's going to happen to us is we've talked about vectors all along. So we've got a vector issue here that is going to come into play. And that vector issue is going to give us something that we call a cross product. So let's kind of do some math here to kind of get us going, because we're going to see this at the end of this chapter and at the beginning of the next chapter. But if I have two vectors, A and a vector B, it's going to ultimately end up in a vector C. So a cross product is also referred to as a vector product. Okay, that's a vector product. And that's why we can get righty-tighty, lefty-loosey when we're using a screwdriver. And also know that A cross B is not the same as B cross A. So I can't just switch the vectors willy-nilly when I do the right-hand rule. So this is why we end up with this being positive in this direction, because my fingers are going to go in the direction of the circle and my thumb is coming out of the page. That's where my right-hand rule comes into play. And then we want out of the page to be positive, or up to be positive. If I were to do it the clockwise way, my fingers would go around the direction of the circle and my thumb would be going in. So if I'm turning it right hand, right, and if I'm driving my screwdriver, I'm doing my right hand and I'm driving the screw into the page. So that's why we use our right hand rule, and that's why righty-tighty, lefty-loosey. Except when we do things like hydrogen cylinders and then we reverse it for safety reasons. So we have some issues that we do things. So this is our vector product that we end up with, and we'll get to that in a little bit. But that's why we're going around the circle. Some things about circles, okay? If I look at my circle, right, we can represent my circle with a radius, that we end up having the radius. The circumference of my circle is 2 pi times the radius. So that's my circumference. And a complete rotation is 2 pi radians, or 360 degrees. Okay, if we do it in terms of degrees, we can do it as 360 degrees radians. We're going to end up working in radians when we start doing calculations, and we'll show you that here in a little bit. The reason we do it is that it makes more sense mathematically than working in degrees. So we want to be in that part. So and if we saw on the video, remember the video where we had the merry-go-round horses, right? The merry-go-round horses. So if I have a big circle, and this is looking at a carousel top down, so here's the center of my circle, and I have an object that's on my circle there, and I have an object that's on my circle here. So this is going to be, we're going to do this as R. This becomes at 2R. And we're going to say the whole thing is 3R here, just so that we have a way of looking at it. Even though the time that it takes to travel around in the circle, the time here is going to equal the time in the next spot, which is equal to the time in the next spot. The distance that this traveled, S, and the distance that traveled, S, and the distance that this traveled, S, are different, right? If I'm going from here to here, that distance is different. And we actually said that if I looked at it, we actually said that the angle was going to be equal to the linear distance divided by the radius. So while the angle is always the same, my S, so my angle is going to be the same for the first one is going to travel S1 divided by R. The next one is going to travel S2 divided by R, and that was 2R. And the next one is S3 divided by 3R. So if I'm looking at my distance, and I'm going to solve for S each one, S1 is going to be R times the angle, S2 is going to be 2R times the angle, and S3 is going to be 3R times the angle. And so my linear speed, okay, my linear speed is going to be S divided by T. The V1 is just going to be R theta over T. V2 is going to be 2R theta over T. And V3 is going to be 3R theta over T. And you can see that I'm certainly traveling in a linear direction faster if I'm further on the outside of the merry-go-round. Still traveling the same angle, but I'm actually going to feel like I'm going faster because I am. And if you think about it in terms of, we've seen it, right? Okay, we've all seen these tricks before. You see it at the rodeo with flag teams. You see it at ice skating shows. You've got the person in the middle, right? We got the person in the middle, and then we got the person over here, and we got the person over here, and we got the person over here. And if we're traveling in a circle, this person is staying put and is just traveling in a circle. This person's doing okay. This person's going right there. And this person's really got to run in order to stay in the nice line or the pinwheel line that we're dealing with. So we've seen it. We've dealt with it. We've even played with it on the playground before. And come the 21st, you'll probably get to see the Rockettes do it, right? The Rockettes always do it in the Macy's Day Parade. You get to see them all move around in a circle. There's usually a thing that they look at. So let's take a circle here, and let's take a tire. So I'm going to use Pirelli tires, all right? And I've got a Pirelli tire here with the letter P on it. And we're going to say that P is going to go around 3 times before we stop. Okay? It's going to go around 3 complete times before we stop. So if it goes around 3 complete times, if we think about it in terms of degrees, we know that it's going to be 3 times 360, and that P is going to have gone and traveled 720 degrees. No, that's not right. 3 times 36 is not 720. That's 2 times 36. 3 times 36 it's going to go around 180 degrees, or 1,080 degrees. I know. So, but if I do 3 times 360, that's what I'm going to get. So we know that. But the next question is, how many radians? And that's going to be a little easier because it's 3 times 2 pi. It's going to end up being 6 pi. Okay? Now, we've all done this. So let's take a roll of duct tape. Okay? We got a roll of duct tape. And we're going to lay out our roll of duct tape. We're going to lay out a strip of duct tape. And we're going to say that the radius of our duct tape, let's use what? This is going to be about, let's see, 4 inches. We're going to say that it's 10 centimeters. Okay? We're going to say that it's 10 centimeters. The radius is 10 centimeters. And we're going to do 6 rolls of the tape. Okay? We're going to make the assumption that, and if I have a fresh roll of duct tape, rolling it around 6 times doesn't change the radius very much, right? So we're gonna make the assumption that the radius doesn't change, but I want to know how much tape we laid out, right? I want to know how much tape we laid out. It does change, but over the course of 6 on a brand new roll of duct tape, the first time off, doing 6 layers isn't really going to change my radius that much. Now, as I get towards the end, 6 layers will. I mean, we know that it will happen. But right now, just for grins and giggles, we're going to say that thin layer doesn't change us very much. And we want to know how much tape we roll out. So if I do that, okay, then that. So 6 times 2 pi, right, is going to give me, how many times I go around? It's going to give me 12 pi times that I go around. Okay, 12 pi times how many times I've gone around. And we have to deal with the radius here, right? So my radius is going to be 0.1 meters. So this is going to be 1.2 pi length. And if I plug that in the calculator, I get 1.2 pi times 3.14. 1.2 times 3.14 gives me something like 3.768 meters. So we can use this to kind of help us out and look at pieces. Okay? So when we give you, now we also know, we've talked about angular position, and we actually showed this. So if I'm rotating and I start here and I end up here, my change in angle is going to equal my angle final minus my angle initial. That's equivalent to displacement, just like I did early on. My change in x is equal to my x final minus my x initial. But if we say we're doing s, I can do my change in s as s final minus s initial. I can look at it the same way that we've been doing it before. We know that velocity is a change in x with respect to a change in time. And we've been doing this. This is x final minus x initial divided by time final minus time initial. And if we want to go back, we can go back to our book, and it's like equation 2.2 back in the book. You know, we learned this back in chapter 2 very early on where we're at. Things are not that different for angular motion, except now I'm going to use this lovely omega. And this is going to be an average because I can have an average velocity and I can have an instantaneous velocity, except now this is the change in the angle with respect to time. Okay, the change in the angle with respect to time. And so that's just going to be my angle final minus my angle initial divided by my time final minus my time initial. All right, now if I'm in radians, the units of this thing are radian seconds. Okay, the units are in radian seconds, except we typically don't write the word radians out. This actually ends up being units of 1/seconds. And we know 1/seconds because we've seen 1/seconds before. On the radio dial, it's a hertz. Okay, it's a hertz. 1/seconds is a hertz. And think about this. Let's look at it in terms of what happens. So if I'm traveling around in a circle, okay, so I start here and I go all the way around in a circle. That is a cycle, right? A cycle on a circle is is one complete revolution. So one complete revolution is a cycle. The period, which we use as a t, the period is the time that it takes to make one complete cycle. Okay, so that's my period. And then we know, because we've done it before, and we've done it in other classes, and we've seen it since we were little kids, at the frequency, which we use as a script F usually, or if I'm in chemistry, we're going to use a funky little letter nu. Okay, we use that funky little letter nu, is equal to 1 over the period. So that's equal to 1 over seconds. So I've got a frequency that's 1 over the period. We've got a complete revolution. So I can actually give you this velocity. This is an angular velocity. Or we can look at it as an angular frequency. How many times does my object go around the circle in a given time period? So if I can say we can do, I can give you the angular velocity of a bicycle wheel by telling you the number of cycles per second. Okay, I can give you the number of cycles per second. Or I can give you the number of revolutions per second. But 1 revolution is equal to what in radians? If I go around the circle once, how many radians have I got? 2 pi. And again, it's because we don't normally think about traveling in a circle, okay? We don't normally think about traveling in a circle. That's just not something that we do on a routine basis. But lots of things travel in a circle. Lots of things travel in a circle, okay? Tires, for example. I'll use tires as an example because that's something that's more familiar, right? Tires, we got tires. So we got tires here. We got our little air spigot. So I got a tire. Any vinyl fans? I got 1 vinyl fan. Any vinyl fans over there, Enid? Oh, you guys aren't awake over there, Enid. You guys are pretty asleep over there. No vinyl fans. That's why I can't do this anymore. Because everybody used to have a record player, right? And if I had a big LP, right, long play, right, LP, long play, if I was in the 1950s, anybody know what it was? '50s. If I were to put except they weren't vinyl, they were actually Bakelite. They cracked. You hit them, they shattered when you hit them on the ground. Anybody know what because if you had a really sophisticated record player, it would give you things that were 33 1/3 revolutions per minute, right? Then you had 70 revolutions per minute. And then if you have 45, you had to change the revolutions per minute. That's how many times my LP went around in a minute. 33 1/3 times my LP would go around in a minute. Now we don't see it anymore, but we still, compact discs, DVDs, those are actually rotated. Those discs actually rotate inside the players. So we actually do rotational motion a lot. And then we have a lot of things that can approximate rotational motion. We can use the same values for rotational motion, which is one of the reasons why we do it. Pendulum, for example, it will do a complete cycle in a period, and it'll have a frequency. So a pendulum will do it. So we can actually look at, pendulums will do it, and springs will do it, because they'll go up and down. And we can approximate that by looking at a circle, which is one of the reasons why we do rotational motion, okay? And I think we actually talked about, so we did omega, so my change in angle is going to be theta final minus theta initial. We also know that my angle is equal to a linear distance r, so S is equal to r theta. All right, we've got that part. We can also look at omega, which is my angular, and that's my change in angle with respect to time. Right, so this is a delta theta divided by delta t. Okay, delta t. And if I do a change in angle, right, if I do a change in angle, I can relate that back to, so let's do this. I'm going to have my change in angle is going to be S1 divided by R minus S2 divided by R divided by delta t. And I'm going to get 1 over R change in S divided by change in t. And we've seen that before. That's velocity. So I can go between linear velocity and angular velocity. And velocity is going to equal R omega. And we know, because we've done it before, I can do what we do called angular acceleration. It's going to equal my change in omega with respect to my change in time. And that's omega final minus omega initial divided by my time final minus my time initial. And that gives me my average. And this ends up being, if I go ahead and do this, I'm going to end up in radians seconds squared. And it turns out I can do the same type of analysis, and if I get R omega is equal to an acceleration, okay, my R omega is equal to an acceleration. So I can look at it that way, so I can convert back and forth. And I think we got here a little while ago, so I'll just write them all down. I can now do the same types of problems that I did before. There's my linear version. Here is my angular version. Here's my change in x. And here's my change in my angle. So all those problems that you thought went away didn't. And we can do problems just like we saw before, except now we're doing them around a circle. So let's travel with this. We've got a wheel here, and we'll look at, we've got a wheel, and it's going to be traveling at a constant angular velocity or angular acceleration of 3 radians per second squared. And we are starting at an angular velocity of 1.5 radians per second, and that's at time t is equal to 0. We want to find the change in angle, or t equals 0 to t equal 1.5 seconds. And we want to find the angular velocity at t is equal to 3 seconds. So that's what we want to do. So I've got that my angular acceleration is equal to 3 radians per second squared. I've got an angle final is equal to initial plus alpha t. So I can do this one real quick, all right? I can do this one real quick because my angle final is going to equal my initial plus alpha t, and this one, my initial was 1.5 radians per second. I'm traveling at 3 radians per second squared. And we're at 3 seconds. And if I do that, I get 1.5 radians per second. And this is 9 or plus 9 radians. Oh, something, did I do something funky? No, that's not squared. That's just radians per second. Because I'm using that one. So it's still 9 radians per second. My units were getting funky. And that tells me I go 10.5 radians per second. I'll give everybody a second because people are still writing down. All right, so let's do the change in angle. My change in angle is going to equal my initial times time plus 1/2 alpha t squared. We had an initial one of 1.5 radians per second. And we're doing it, this time we're going from 0 to 1.5 seconds. So I've got my 1.5 seconds plus my 1/2 3 radians per second squared, and I've got my 1.5 seconds squared. This time I am doing seconds squared. If I plug that into the calculator, I get 2.25 radians plus 3.38 radians gives me 5.63 radians. But guess what? We don't necessarily have a good feel for what that is, right? So let's ask the question, the number of revolutions that happened. Okay? The number of revolutions that happened, because we don't think about radians per second. So let's do that one. So I get 5.63 radians, and there are 2 pi radians per revolution. So my radians cancel, and I end up with revolutions up top. And when I do that, it's become, oops, getting ahead of myself, 0.9 revolutions. Okay, so let's do another one. All right, this time we have a disc. And if you're an ultimate frisbee player or play frisbee golf, you can think of a disc as a frisbee, all right? All right. The disc has a diameter, and we're mean, cruel, and wicked like this on you. Has a diameter of 30 centimeters, and it is going to be rotating at a constant angular acceleration of 2.25 radians per second squared. We're going to start at rest. At t equals 0 with a line drawn from the center to a point P on the rim. P is located at 50 degrees from the positive x-axis. At time 2 seconds, find the angular speed of the wheel or the disc. I'll write disc because it's easier. The linear velocity and the tangential acceleration of P, and finally the position. And I bet this looks like an awful lot of the homework problems. Looks kind of like the homework problems, right? Angular speed of the disc, the linear velocity, the tangential acceleration. So first thing is you got to figure out what the heck the sentence is saying, right? Well, the first thing that we know is we got a circle. We got a disc, right? So I'm going to draw my picture. There's my picture. I got my disc. It's a kind of ooky circle, right? At this point, it's an ooky circle. We've given you, mean, cruel, and wicked, we've given you a diameter, right? We've told you the diameter is 30 centimeters. All right, so my diameter is 0.3 meters because probably I'm going to want to be in meters instead of centimeters. And I really need the radius. So my radius is the diameter divided by 2. So I'm going to take my 0.3 meters, divide by 2, and I get 0.15 meters for my radius. So that helped me out. Okay. When in doubt, draw the picture to start. Okay, so that's the first picture. The second part is I got to figure out where this P is, right? We told them we're going to draw a line. And I got to know where this P is. And so I'm going to put in on my picture, I'm going to draw a line. And we're told that this is 50 degrees. Okay, we're told that that's 50 degrees. So that's where we're starting from. There's my letter P. Okay, and we're told that my angular acceleration is equal to 2.25 radians per second squared. So information that I know so far is that I have the radius is 0.5 meters, and I have an angular acceleration of 2.25. And we know my initial velocity was 0. So the first thing we want to find is we want to find the angular speed of the disc at 2 seconds. I've got a toolkit, just like I've had before. Angle final is equal to angle initial plus alpha t. I have my change in angle is equal to my angle initial times time plus 1/2 alpha t squared. And I have angle final squared is equal to angle initial squared plus 2 alpha times my angle. There's my toolkit. So, start out with the easy one. Angle final is equal to angle initial plus alpha times t. This is 0. We have 2.25 radians per second squared. And we want to find it at 2 seconds. So we've got that. So if I put that into the calculator, I get 4.5 radians per second. Now we wanted to find the linear velocity. Well, my linear velocity is equal to the radius times my angular velocity. So that's going to be my 0.15 meters. And I get my 4.5 radians per second. And this is where things get a little interesting in terms of units, because we typically don't write down radians. So I'm going to end up in, when I multiply those together, I get 0.675 meters per second. Then we wanted what they called the tangential acceleration. So let's talk about that for a second, because we've already seen if I'm traveling around in a circle like this, we know that there's an acceleration that goes towards the center. And we call this the centripetal acceleration.
You need to scoot the paper up, please.
There we go. The centripetal acceleration.
Better. Thanks.
And we saw that that was v squared over r. So my centripetal acceleration is v squared over r. My tangential acceleration is this one. That my a tangent, and usually we do the tangent right there, so a tangent is equal to r alpha. That's my tangential acceleration. This is my centripetal acceleration, and that's AC. So if I go ahead and plug this in for this one, I'm going to get my 0.15 meters, and I'm doing it times my 2.25 radians per second squared. That's going to equal my 0.34 meters per second squared. That's my tangential acceleration. But I also have a centripetal acceleration, so I have two accelerations. And if you think about this, I'll give you guys a second to write stuff down. So let's kind of look at what we've got. So if I've got something that's traveling in a circle or around a curve, because we've been doing this, I've got the center-seeking acceleration, which we call a sub c, which is equal to v squared over r. Now I have a tangential acceleration that's equal to r alpha. So essentially what I have happening to me is I have two components of an acceleration. So I can have two components of my acceleration, and we've done this before when I have two components, that this is going to be the square root of my centripetal acceleration squared plus my tangential acceleration squared. And that would be the total acceleration that's on my object. And I think you've got some homework problems that actually look at this. Okay. And we've already figured this out. So if I have my tangential acceleration, and we figured it out as 0.34 meters per second squared, my centripetal acceleration is v squared over r. But we already figured out my linear one, because we figured that out. That's 0.675 meters per second. So my AC is 0.675 meters per second squared divided by my radius, which was 0.15 meters. And if I plug that into the calculator, this gives me 3.03 meters per second squared. And now I can get my acceleration total is equal to the square root of 0.34 squared plus 3.03 squared. This is going to be in meters seconds squared. If I do that, I'm going to square that plus 0.34 squared. Gives me 3.06 meters second squared. That would be the total acceleration on the object, even though the problem didn't ask us for that. Then the problem asked us for the change in angle. So I can do this. And that's going to equal, my initial velocity was 0, so that's 0, plus my 1/2, 2.25 radians per second squared, times 2 seconds squared. If I plug that in, I get 4.5 radians. But we want to know the final position. This case, I have to know where my initial position was. Give everybody a second. So we started at 50 degrees. Okay, so my change in angle is going to equal my angle final minus my angle initial. We know the change in angle was 4.5 radians. We don't know the final angle, but we knew the initial angle, and I'm going to go ahead and put this in here as weirdness, 50 degrees. Well, we got a problem. We're in mixed units, so I have to figure that out. So I can do a couple of different conversion factors. I'm going to use pi over 180 degrees, because if I draw my circle, okay, 2 pi is 360, or pi is 180. So I can use either of those conversions if I want to. So I'm using that one. And if I do that, this becomes 0.873 radians. So my angle final is going to be my 4.5 plus 0.873. And that's all in radians. And that gives me 5.4 radians is my change in angle. So what's happened here is I started at a point right here where that's 50 degrees, or that is 0.87 radians. It's going to go around some angle, and we want to know what that is. And I found out that it was 5.4. Well, to give ourselves some kind of feel, does that make sense or not make sense? I'm going to convert it back. So it's 5.4 radians. And it is pi radians, 180 degrees. And if I do that, I'm going to find that it's 309 degrees. And then if I were drawing my picture, it would look like this. But sometimes, because WebAssign is mean, cruel, and wicked that way, it asks for that angle. Because it'll say, what's the angle measured from the negative x-axis? And you go, okay, that's got to deal with that. So that's 360 minus 309. And that gives me what? Because I can't add today, add or subtract today. 51 degrees. This has a practical application. If I have a tire and I have my filling spot in the wrong place, because I'm driving one of those vehicles that my tire's hidden, how far do I have to roll my wheel in order to get my filling spot down here where I can use it? And we do that in our heads, right? We go, okay, I got to roll this far in order to get the spot there. We do that in our heads a lot. We talked about that. We talked about that. Talked about a right-hand rule. So let's look at our right-hand rule just a little bit more, because really what this is telling us, because when we're dealing with our angular motion, I'm doing my right-hand rule, so I'm going to draw my picture here. What really happens is my angle is going to end up like this if I'm rotating in that direction. And if I'm rotating this direction, that's going to have me going that way. And I'm guessing brains are full. I got an affirmative over here. I'm getting brains are full because I want to start torque on Friday. Yay! Any questions? Anybody have? Hi. Fine. Take it. Yeah. I don't need.